Today I am going to discuss one very important thing about the NMR peak intensity. So this is every day I am giving you some idea about the basic theory of NMR. Today we are going to discuss you the peak intensity. So actually intensity depends upon the B0, actually applied field, how much applied field uh, put on the used in the magnetic machine. So that, depending upon that, the cost of the NMR spectra machine depends. So you already heard about that this is a 300 megahertz machine, NMR machine, 400 megahertz, 60 megahertz, 100 megahertz, 200 megahertz, 600 megahertz, and 800 megahertz. It's already 900 megahertz NMR spectrometer also available this time, but that is too much cost. Uh, why this cost increase due to megahertz? Because its need to create that much field, magnetic field, we need too much very high power superconductor to create that type of magnetic field. So as you increase the magnetic field, the uh, population population difference between alpha state and beta state. Alpha state and beta state, as we discuss in our theory class, that's depend. So if you increase the B0, that is high magnetic field, then the population difference is increased. So if you increase 60 to 100 megahertz machine, magnetospector, electromagnetic spectra, or the uh, NMR spectra, then this difference between alpha and beta state, it's increase. So if increase the, so more the difference between this alpha and beta state, the population difference is increased. So suppose in a 60 megahertz, as we know, the NMR spectra absorbs radio frequency, because of that is very less amount of energy, very less amount of energy. So it is, population difference is alpha and beta state is in normal temperature, it is very less, almost equal, almost equal. So this is alpha state and beta state. Now if we increase the applied field, that is V0, then how its population difference between two states occur in the um, Boltzmann distribution. So we know this Boltzmann distribution is n beta by n alpha. So if we put in Boltzmann distribution, all at n alpha and n beta, all other fractions are means this is as ratio, all are means both side, upper up and down, both are actually divided with the same. What is the not the other factors that still is there, that is n beta by n alpha equal to e to the power delta E by RT. Delta E means energy difference between two states, and RT both are constant. We know at a constant temperature, room temperature, that is 25, and T and R is constant. So R E equal to H nu, that is H nu B0 by 2 pi at uh, 300 megahertz, that is 70500 Gauss. 300 megahertz equal to, that is 370500 Gauss. Now if we put the all the value here, n by n alpha, n alpha, n beta by n alpha, then e0 e to the power minus 6 point, this is we know the numbers, all the numbers, h equal to 6.63 into 10 to the power 30 minus 34, and delta is equal to 26753, and b0 is 300 Gauss, 300 megahertz, that is 70500 Gauss, and rt, we are putting this value and 2 pi. And if we find this value of this number, that is equal to point, the ratio, actually ratio is equal to almost 1, see, almost 1, 0.9999945 149999952. So it is very less, actually almost 1. So if we take 2 millions of proton, 2 millions means 20 lakhs, 20 lakhs proton, 2 million of proton, the difference between alpha state and beta state, lower energy state and upper energy state, that is only 48 at 300 megahertz. So the energy absorbs and peaks, the peaks particular per particular peak, we are getting the energy for only 48 proton, 48 proton you can see. So 48 same proton, same type of proton, we are discussing about the same type of proton, means same peak. Suppose it is we in NMR spectroscopy we are getting a peak on 1.2. So 1.2 for that particular proton, if 2 millions of proton is there, only out of that 2 million proton, 48 number nuclei will give this, that 1.2 signal. And as similarly for all other proton also. So if we take at 500 megahertz machine, 500 megahertz spectroscopy machine, that is 1 lakh 70. This is actually 1 lakh 1 lakh. This is actually 1 lakh 17,500 Gauss. 1 lakh 17,500 Gauss, that is equal to 500 megahertz. There, this C number is little bit less than here. So ratio n beta by n alpha equal to 0.9919. That is in 2 million proton. Out of 2 million proton, only 81 proton will give now this signal. 81 proton will give the a particular signal. We are discussing for a single peak. So for single peak, if there are 2 million proton, only 81 proton for that peak we are getting for only 81 proton. This is the calculation about Boltzmann distribution. From the Boltzmann distribution, we can have this calculation. So now you can have an idea then how these if we put the more high power NMR spectrometer, then we are getting better NMR, because this population difference is increasing according to the increase of the megahertz, that is putting how much B0 we are applying in the in visual applied field, we are putting the sample inside that spectroscopy. Similarly, other calculation, same, you can see now the frequency, how much frequency that megahertz we are keeping, we are running this particular sample uh, in different megahertz machine, different megahertz spectrometer. For 20 megahertz, there are only three protons, so the spectra will not be that much clear. See, 40 megahertz machine only 6, 60 megahertz machine 9. So 60 megahertz machine, you can you supposed to means imagine just around 20-year back, at 25-year back, at most of the institute having 60 megahertz machine, 80 megahertz machine, and 100 megahertz. Most of the 60 megahertz machine there. So earlier the book whatever you are reading, a little old book, that all that NMR run in the low frequency, that is 60 megahertz, 80 megahertz, 100 megahertz most of the time. That so these days, you will not get this type of machine, 60 and 100. Most of the 100 is still available, but 200, 300, and 300, 400, 500 megahertz spectrometer is there. So see the population difference is how much increase. In 600 megahertz, you will get the population difference is 96. So so you will get 90 on the particular peak, 96 proton absorb the energy, and you will get the peak for that 96 proton absorption of 96 proton. 96 proton will flip from alpha state to beta state. Alpha state to beta state, and when it relaxed from the beta state to alpha state, you will get the NMR peak. So particular, if you increase the magnetic field, that is B0, you will get better and better NMR, and the peak separation and other property will show very clearly. So let us now today, let's see for 2 3 NMR problem today. Different type of problem. Earlier, whatever we had discussed, last all the videos, this is little bit different. Actual problem, how NMR can be solved. See, you will get this type of problem maybe in your exam, different exam, and books also. See, on spectrum of the compound, on H spectrum of the compound, C8H8O2, C8H8O2. So if you calculate the BD, means how many double bond equivalent is there. uh, so BD, how many double bonds are there? You can have that idea that how many double bonds are there, and you will get these numbers here. Sorry, see this one. So there will be like that, 9.78, one peak area is, that is intensity is 1.01, and 2H singlet. This is 2H singlet. And C 7.75, there will be two proton. That is definitely aromatic proton. 2HD 7875, and 6.90, there is another um, another two proton is there, 2.01, that is two proton only, and the that is also doublet. So we have aromatic proton two doublet. So definitely two doublet, and there is no more an aromatic proton. So definitely here we can write the NMR of like that, this. So suppose, uh, let us draw here. So right, unable to write. Okay. So definitely one benzene ring is there. You can calculate the BDE and you will have 4, that BD is 4 for that particular molecule. So one benzene ring is there, and definitely it is para substituted because two doublet, you got two doublet, see, two doublet, two doublet and only two peak aromatic region, only two peak. So we have a structure like this. So already 4 proton gone, 4 proton, see 4 proton. So this is this 4, 2 and 2, 2 and 2. This actually this is you can see little bit high, but that doesn't matter. Peak area is as we discussed last in the last video, that peak area is calculated integral value is inside area, total area of the inside. So this is 2, this is 2. So how many? Already 4 proton gone. So we can see a aldehyde peak is there, one aldehyde peak, and another 3 proton. This is CH3. This is CH3. So CH3, and the value is 3.9. 3.9. So if it is means toluenic proton, the toluene proton is coming at 2.2, like that, 2.2. So but it is not, it is almost 2.9, 3.9. We earlier discussed in the benzyl proton, and the last yesterday also in the lot of video we have seen when the methyl or methane is attached to oxygen, that time only the CH2 and CH3 peak is coming at around 4. Just you can remember in the benzyl protection, the benzyl CH2 proton, benzyl alcohol CH2 proton came at uh, 3.9, 4 o'clock, 4 ppm, right, like that. So this is yeah. So aldehyde, for aldehyde, one oxygen gone. So aldehyde, we know we have the aldehyde here. Aldehyde, one aldehyde proton. This aldehyde. So we have this one, this hydrogen, this hydrogen, this hydrogen, and this hydrogen. Definitely two different type of substitutes are there, as the value is too much different. You can see the value. How much value? This is 6.9 and 7.2. Means you can see 7.75 means very much electron withdrawing. Very much electron withdrawing. So 7.75. So aldehyde group is there directly. So we can write this aldehyde here. See, we can write aldehyde here. Now we find that the peak came at 3.95. The three proton came at 3.95. 3 proton. That means definitely that is one singlet is there. So this is there, there. So and that is not directly attached with the directly attached. Then this is 2.3 or 2.4 maximum, that not beyond that. But this is 3.9. So definitely this is the group. So already see, there are 5 proton gone, 5 or 3 8. Oh, so if you, and no other carbon is also there. So carbon, how, see, already 6 carbon, 7 carbon gone, and 1 8 carbon. We don't have any other element to attach. So we can write like this: CH3, CH3. So like that you have to solve the problem. So let's see what is the answer of this molecule. See, this is the answer, this is the value, this is the solution of that spectrum. This is C aldehyde proton 7.78 singlet, integral value is aromatic proton 7.75, 7.75, 6.90 doublet, both are doublet, integral value is 2, both are 2.0 and 2.1, and 0.0 methyl 3.77 singlet, and 3.1, that is, so this is the solution. Now I want to show you we have done right or wrong in the theoretical value. Let's see. So first 1 2 molecule, we can I want to give you a clear idea about this. So that's why I am solving this problem with you. Let's draw the molecule. Let's draw. This is the molecule we solved. And let's see the NMR spectra of this molecule. See. See, same. This is 3.78, 3.78, 7.88, 7.88, 7.118, and 9.8. See, same. Pattern is same. Value may be little bit different. Pattern is same. See, this proton shown at 6.98. Here it came at 7.18, and this proton, uh, see. So 6.90, 7.75, 9.78, and 3.77. See, this came at 3.83. This proton came at 7.17. This is 6.90 actually, actual value. And this value is 7.88. And this one is 9. So this is the solution of the compound. We did perfectly. Let's see another problem. Huh? This is actually you can have a clear idea about this. We discussed a lot of time this type of NMR peak. So C4H8O2. This is C. Chemical shift is 4.13. 4.13 means the two proton, and 2.0 man, that is 2. মানে 2, that is keto type of proton. And 1.15, that is the terminal CH3. Here no character has been shown, but from the spectra you can clearly see the clear view here, that this is a triplet, and this is a quartet. See, this is a quartet and this is a triplet. So quartet and triplet, you can see it's CH3 CH2. Definitely this is the CH3 CH2 group is there, and one methyl group. So you already solved the molecule actually. 3 This is 3 and 2 5. This is 3 and 2 5 attached, and this is CH3 and 2 oxygen is there. Let's draw the molecule here. What we got? We have CH2 and CH3. And we already have a keto proton, keto methyl. That is 2. That came at 2. This will come at 2. Delta value is 2. And this is CH3 1 point. I told you a lot of time that this terminal CH3 will be triplet, definitely triplet, and 1.2 around, 1.2 around, 1.15 that came. And this will be higher region. This will be in higher region. So like this. So like this, not directly keto attach, but this one. Now, if you solve the problem, C4, H8, and O2, and O2, O2. So, see, 1, 2, oxygen, 3, 5, and 3, 8 proton, and carbon how many? See, 1 carbon, 2 carbon, 3 carbon, 4 carbon, already solved. So, if we connect this one with this one, so this, that is simply CH3, CO, and CH2CH3. So see, CH3, CO, CHO, CH2, CH3. Let's see another problem. This is spectra of C5H10O2. C5H10O2. See the value here once again. 1.92 pK. This is chemical shift is 2.20 and 1.17, and this is 0.78 and 3. Mean definitely this is a triplet. This is a triplet, means that attached to a methyl group, methane group, CH2 group. This methyl means that is a aldehyde, means aliphatic terminal CH3 group attached to CH2. And this chemical shift, it is 11.8. 11.8 means definitely it is aldehyde or acid. So this is aldehyde, means acid. Now aldehyde is not coming at 11.8. This is definitely acid type of protein. So now we have an idea that this molecule having a terminal CH3, which is attached to CH2 group, and there are two CH2 group. 2CH2 group. So you already have that problem solution. CH3, and that is attached to CH2. Again, if you put another CH2, because this is also multiplet chem. See, multiplet, and this is singlet, one terminal hydrogen you have to, and this group is, see, there are 5 carbon, but there are 4 type of hydrogen. So definitely one carbon is without hydrogen. One carbon is without hydrogen. So let's take a CH2. This group is already there because the terminal CH3 is there. That is delta value is point how much? 0.78 মানে 0.78 delta value মানে this is 0.78, and this is they definitely triplet due to this. So you can say that this group is already attached to another CH2 because another CH2. So how many? See, it's CH3, CH. Uh, so this will be multiplied now. This will be multiplied, and this will be also multiplied. Uh, See. So already we have done how many proton? Three, five proton. Uh, Five proton gone. So another five proton and one six proton. Total proton number you see. Three, 4, 7, 8 proton. This is actually, I think it is wrong. Value. So two proton is missing here. So okay, this four, this is four actually. Multiplets, and this is four, not this one. This is four. This is four actually. Now it's came. Four. This is four proton. So in this spectra only you can see this is two to four proton, two to four proton, and this is another two. So this so another CH2 group is there. Now you can see three already six and nine, three nine proton. So another carbon we is there. Now already five carbon is there. 1, 2, 3, 4, 5. And how much came? Problem is five carbon gone. Already nine proton also gone, and two oxygen is there. Two oxygen. One oxygen already we attach. So another, this is acid group, we know, as we told earlier, 11 point more than 11 value is coming, that is acid. So this is the problem. This is the so we last time we discussed that this type of proton is coming at 1.4 around. So 1.4, this is a little bit higher because this is directly attached to keto type of carbonyl type of bond, and this is acid. So little bit more shift, a little bit more shift. See, 1.9, 1.92. So 1.92, this is carboxylic acid attached group. So this came at 2.20. So a simple carbonyl is coming at 2, but this is 2.20. And this is 0.78 due to long chain. Due to long chain, the carbon, this acid group is too far from the CH3. If this is here, then definitely on simple one carbon away, this value is coming at 1 plus. So too far means we can say this group is far from the any far from any electronegative or electron withdrawing withdrawing group. So it is coming at 0.78. Now let's see in how it's come in the NMR NMR theoretical NMR. So five carbon done. 5 carbon done, 2 oxygen done, here 1 OH. So this is the molecule we have drawn. See the value. See the value. It is showing at 11. Practical value is 11.2, and this is 2.2. Practical value is showing 2.20. This is 1.52, 1.31. See, 1 point, and this is 90. Practical value is 0.78. So pattern is same. Value, theoretical value and practical value definitely will come, because software cannot be that much perfect as the molecule is showing in the spectrometer. This is a software just. We can have a clear idea about the spectra of that particular NMR spectra of that particular molecule, but we cannot have exactly same NMR uh, in the theoretical, theoretical in the software also software. So this is the difference. Now you can have a idea about the NMRs. uh, three spectra we discuss, and see this is the solution. CH3, CH2, 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 COOH, and see, this is exact for perfect NMR spectrum. So that's all already, almost. We can have another NMR spectrum, because we can do another solve problem. This is another molecular NMR spectra. This is C4H6O2. C4H6O2. We first see. Let's see in the how many protons are there. Six proton are there or not? How many proton are there? That should match with this one. Earlier we had a here by mistake we have written a 2. So we should calculate. Here 6 proton is there. 6 proton is there or not? See, 3 1 1 1, 3 1 1 1, like that is there. So there are already 6 proton is there. So 6 proton is there, and there are we can see a singlet. This is singlet. This is singlet. This is singlet. All are singlet, and two O2 also, two O oxygen also there. Two oxygen are there. There are 4 type, means 4 carbon, 4 6 hydrogen, means definitely the CH3 group. This is CH3 group is singlet, means there will be no there will be no eh, is there. So there will be, actually there will be no splitting. There is no splitting at all. There is no splitting. So how it is possible? And from this, we can see 1.90. 3 proton is 1.90. 1.90, 3 proton. 1 point means this is not keto, but uh, this is not keto, and there are 4. And another important thing is the C6 6.66, 1 proton, and 5.62 another proton. 5.62 another proton. So definitely this molecule having a double bond. This molecule having a double bond, and a double bonded attach hydrogen. uh, double bonded attached hydrogen, and another also is there. So it is definitely, we can write like this. uh, s- Definitely this is a double bond. So double bond, and we have how many? So one, two, three, four, five. How many protons are there? How many carbon? There are four carbon. So four carbon. So definitely, and three proton. So uh, we can write double bonded means one hydrogen. We can write here one hydrogen. So gone one, two, three. One type of hydrogen. Another is CH3. So how many? So one carbon, two carbon, and three carbon. And there is value. Let's see the value once again. There is a chemical shift of see how much? 12.5. 12.5 means another acid proton. Another acid proton. So another acid proton is there. So acid we can write here CO2H. CO2H. So this is CO2H gone. So now CH3. Now CH3, how can we attach the CH3 with the molecule? So how many? One, two, three, three, and that is CH3 also singlet. That. So if we write here and here hydrogen. So actually, sometime this type of proton, this will be singlet, uh, and this will be singlet, and this is also singlet, and this is will be also singlet. You can write another isomer, uh, isomer. So this is hydrogen. If you write hydrogen here, this is hydrogen here, and this is CH3, and this is CO2H. In this case, here J value is definitely this should be doublet. This should be doublet here. So trans is not possible, maybe not possible. So let's see the problem solution. This is the solution of that compound. So whatever we have written in the earlier, see. So this is the solution. So this is the right. This is the right one. And I want to show you this molecule in the uh, chem draw. It may be a little bit different because I think in the chem draw the vicinal uh, the the hydrogen attached to same carbon should be splitted. In theoretically, it should split theoretically, and practical value it didn't, 'not. 'Didn't. 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 'Didn't just I will take only 1 minute, another 1 minute, because the video is going to be too long. That's why uh, once you start something, so it's taking some time, and in between it's coming to discussion with some other things, so you cannot stop in a particular time. See the value now, exactly whatever we discuss. Both the proton are showing different, and both are singlet only. So that coupling is not do too much effect to each other. So that is not actually coupling with each other. So no J value is there. So all are singlet. CH3 is singlet, and this proton is singlet. All are singlet. So it is okay. So it is matching actually. So that's all. Thank you. Thank you very much. You practice, means every NMR I am showing here is very important. This type of problems are coming in the MSc and BSc. Most of the cases in MSc, uh, MSc question paper and MSc problem. Also sometimes BSc also, not spectra, but sometimes this type of problem is coming in the BSc class also. Some for confusing, some IR value, you can have an IR value of this compound, that there is a strong absorption at 1700 in 1745 in the IS spectra, and there is a broad spectra at 3300. So this is the characteristics of the peak, the IR spectrum. And this compound is absorbing UV at suppose 225. So it is UV active. This is IR active. IR is showing two strong peaks at 1700 and 3300, broad peak, and NMR spectra all are singlet. So find the structure of this compound. Find the structure of the compound. So this type of problem may come. So only NMR, by NMR we solve this problem. So if you having some more data, it will be more different. But you have to clarify after writing this structure. You have to clarify why this IR spectra is showing 1700, 45 or 40 around. What is that? That is carbonyl, carboxylic acid carbonyl. And another is the broad peak at 3300 around, a broad peak, that is OH of acid, broad peak. And in the UV spectra, the 220 around coming is the alpha beta unsaturated acid. So alpha beta unsaturated compound is UV visible, UV active, actually UV active, and it is showing in the range of 220 around. So you have to clarify that. And with the NMR also you have to clarify that this is a acid group, because it came at 11 plus, and this is CH3, which is singlet, because there is no adjacent carbon hydrogen, and two uh, this is a rigid structure, as a double bond and rigid structure, and the compound is actually uh, the hydrogen cannot the CC double bond cannot rotate. So both are hydrogen and different absorption, electronic influence, the electromagnetic influence surrounding the hydrogen. Definitely, this hydrogen is attached to same side as CH3, and this hydrogen is same side as COOH, and definitely this will be means electronically, this is more is close to the OH, and radiation exposed to more electron radiation, and influenced by the COOH group. So you have to clarify at the time of solving the problem. You have to clarify all the things in that particular NMR. Whenever you are writing the structure, you have to clarify the uh, why you have written this structure. So if it is a means suppose 4 mark question, so you have to write all these things. 4 mark question, so singlet, why this methyl is singlet, you have to write. So thank you very much for today. Thank you.